Okay, well, I guess we will start session number 2 right on time, I guess. So we have Ollie telling us about CMS analysis and data reduction with Apache Spark.
All right, so thank you for inviting me for this parallel talk, and hi everyone. So my name is Ollie. This is going to be, hey Dan. So this is going to be a follow-up talk of what we presented at CHAP. And these are our efforts to use Apache Spark for analysis with CMS data and the problems and the solutions we encounter and find. So I don't think I have to tell you a lot about what we do, but maybe there's somebody who's not doing particle physics or hasn't done particle physics. So we're going from particle collisions, using big computing, to, in the end, physics discoveries. I mean, this is what we're here to do, and this is the kind of depiction of our physics. It's a plot, right? It's a plot that compares data with a simulation, and then you see something that doesn't fit, you add something to the simulation, and all of a sudden everything makes sense again, and you discover the Higgs boson. So big computing, in general terms, is used in the whole way from taking data or simulating data up to the famous plot. And in between, you have the algorithms to reconstruct the raw data that comes from the device or from the simulation, and then the analysis software that usually takes the reconstructed information and then converts that into plots and tables, and this is what we put in our papers. If you look at a little bit more in detail how this is organized, I usually separate that into a central part, which is done usually by the experiment or by the collaboration in one go for everyone who is member of the collaboration. And then I call it the chaotic part, where every analyst or analysis group who is really pursuing a specific analysis topic is looking at parts of the data, is looking at parts of the simulations, and deriving their plots from them. So this is what we're talking about, and this is what we're trying to optimize. So this is very CMS specific, and the border between central and chaotic usage of the data is fluent. In Atlas, for example, it's a little bit different, but we all, in the end, try to do as much physics as possible in the shortest amount of time. And I call this, we want to minimize the time to insight. So from raw data to the insight, that's what we want to do. And analysis, for me, is really a conversation with the data. You want to ask the data a question, you want to get the answer back, and then you want to change your question or ask a different question so that in the end you get to a physics result. And therefore, interactivity is really key, because the analyst wants to play with the data and interact with the data. There are many different physics topics that are concurrently under investigation in big collaborations. So you have a whole variety of different analyses going on at the same time. And they all look at different slices of data that are relevant for each of these analyses. Different Monte Carlo samples, different trigger samples, all this is going on in parallel. But programmatically, the analyses are usually the same, because they have all the same analysis steps. They do skimming, which is dropping event in a disk-to-disk copy. So this is when you make an n-tuple. It is slimming, which is dropping branches in a disk-to-disk copy. That's at the same stage. And then you have filtering, which is selectively reading events into memory, only the events you're interested in, or pruning, selectively reading branches into memory. And these are kind of the 4 basic transformations that you do when you do analysis. So what we want to do is we want to exploit the new toolkits that are out there, open source toolkits that are very much happening in industry, where they really go now from petabyte to exabyte samples and do these analysis types of things. Previously, I mean, 10 years ago, we were the only ones who were doing this, but industry really caught up and surpassed us, and this is what we want to exploit. So our goal is to use these technologies, reduce time to insight, but also look a little bit further. So to look at, really educate our grad students and postdocs using these industry-based technologies, because I think that improves their chances on the job market outside academia, which we always have to take into account, because our field is not that big that we can employ all our postdocs and grad students. And it also increases the attractiveness of our field. And we are a part of an even larger community that we are right now in the tools that we're using. So that's the goal. And we're trying this in two different thrusts. The first thrust is a really purely usability thrust. That means that we want to do an end-to-end investigation to conduct CMS physics analysis in Apache Spark and produce publication quality plots and tables from the CMS data using this open source. I know Gordon is already smiling. This is not actually simple because you first of all have to do it, then you have to convince your collaborations that you actually did the right thing. But that's the goal. I mean, that's what we're working on. Thrust 2 is a little bit more applied. So this is called the CMS Data Reduction Facility. This is a joint project between CMS, CERN, OpenLab, and Intel, where we want to demonstrate the reduction capabilities of Apache Spark. We have an ambitious goal. We want to demonstrate that we can reduce 1 petabyte of input into 1 terabyte of output in about 5 hours. And if you think about that, that would be very cool for every analyst because they could do analysis and within the night essentially do new n-tuples. So the whole string of making n-tuples and smaller n-tuples on that would go away. So we reported on that at CHEP. We did a usability study, and here the first step we did is we used the conversion route, so that we converted our root file into a format that Apache Spark can understand. We implemented our analysis in Scala, which is a language that Spark works well with, and we did the processing in Spark, and the result was that actually the Scala analysis was structurally a lot simpler than what you do in root. And it was easier to port. So we could move the same analysis to any other Spark cluster very easily, while root-based multi-step reduction analyses are harder to move from one facility to another. The performance comparison was challenging, so we didn't actually achieve a real apples-to-apples comparison. But what we could say is that it's at least not orders of magnitude slower than what we do right now. So it is promising. And so we were continuing to look at that. But the lessons learned for me of these tools is that analysis tools, especially plot, how you make plots, are not easily transferable to this map-reduced style processing of Apache Spark. And everyone hated the conversion. Everyone really said, oh, I don't want to convert my data to use this new technology. I really don't like that. So as long as you don't do anything about that, I'm not even going to look at that. So that's the two things we actually worked on. The first thing is we did this together with Diana, and Jim Pivarsky, the main architect, sits in the back of the room. And here we talk about histogrammer. And histogrammer is a way of doing histograms the map-reduced style. So you know that Spark really manages concurrency. So it actually takes the event loop away from it. And you program more in a functional way. This is what we also discussed with Gordon and Kyle in Amsterdam, that this is possibly coming. And histogrammer is designed for this environment. It has a functional interface. It fills histograms by passing lambda functions. And it does the same as transformations in Spark. So histogrammer fills a histogram data structure. It doesn't do the actual histogram, but it fills the histogram data structure in a map-reduced way, and afterwards you use you convert it into your favorite plotting tool and plot it. So I asked my postdoc to do that. So he struggled the last night to actually make a plot, and this is the plot. We did the plot on Spark with histogrammer, got the data out. Then he used something which is called bokeh. I don't know what this is. This is a very favorite plotting tool, apparently. I put a link here. Yeah, you know, I mean, it's these young people, they use these things. And it's designed to work in Apache Spark and interface directly with histogrammer. So actually, Jim and the team wrote instructions how to use that. And there are also other options. So, example, you can also use PyRoot to do the same thing. But it is made in a map-reduced way, and this is the important thing. The next thing we worked on, again with Diana and Jim, is the the conversion problem. We didn't want to convert the data into something that Spark understands. And this is actually very clever. It's called Spark root, and it reads root files directly in Apache Spark. So you can put your root files somewhere that Spark can reach, and you can read it into data frames and use it in Apache Spark directly. Connects root to be able to read the root tree and infer the schema. You don't have to tell it about the schema. It is inferred for you. You just open it. And then you manipulate the data via Spark's data frames, data sets, RDDs, what you need. We, in addition, work now with CERN IT to read the data, first of all, from HDFS that is inbuilt, but now also from CERN EOS through an XRootD connector, which is called the Hadoop XRootD connector. And I don't know why this is not coming out that well. But here you see some examples where a root file was opened and the schema is just inferred and you can read all the branches. So this is now something where I just want to give you a glimpse of that this is actually working. And this is actually performing well enough that we think that this is the way forward. So what you see here is a test on a standalone infrastructure. We have a dedicated test Hadoop cluster, which were 3 machines, one name node and 2 data nodes. We use the XRootD connector to just copy from EOS to HDFS, just to see what the performance is. And it is limited by 1 machine. This goes to 1 machine, and you see that it's not using all of the available network, but it is fast enough to say that it is not preventing the system to work in a reasonable way. You see, when you copy 200 gigabyte of text, you get a gigabyte per second Parquet, possibly due to fluctuations in network load and all that, 800 megabit. And then if you change the EOS instance, you see that you start to see different effects, right? You see that if you go to EOS public, which is more heavily loaded by people that do heavy copies, you see that you have large fluctuation and you have a lower copy rate. On the other hand, if you then use Spark with the connector on files from EOS, you see that you get actually reasonable rates. You get up to 2.3 gigabits per second when you use from EOS public, 6 to 9 gigabits if you read Parquet, and this is because also Spark is optimized for Parquet. Text is a little bit slower. So we say it performs reasonably well. Copy tests are limited by public performance and copying into a single machine. And we don't see any showstoppers visible in the standalone test, but of course we need to optimize and tune the connector now. Then we go to the cluster. We use analytics at CERN, which has 36 nodes, and we try to ramp up the input data that we have. We have a test suite that runs the input and I think makes Daimion plots and writes out a small n-time. Half a terabyte for now. You see that a single executor, so you really have 1 core doing that, takes about 4 hours to do a half a terabyte, or 10 hours for half a terabyte when you go from EOS. This is not very fast, but this is also not the point of this. The point of this is that really the connector survives and reads well larger amounts of data. If you then go to parallelism, that means here in this case, we have 40 executors, 4 cores per executors, so you go to 160 cores. You see that the runtime for the same half terabyte goes to 5 minutes from HDFS and 19 minutes to EOS input. And there are many different input parameters that can be changed, network load, load on the cluster, all that. But you see, this is already in the area where we start to see real interactivity, where we really can work very fast. So the problem, of course, is that you have then a lot of different tasks running in parallel. You have tasks that run longer or that run shorter. And these are the things we have to now look into. We're still at the point where the connector is 2 to 3 times slower than if you read it from HDFS. But this is something we're working on now in performance tuning. But this is working. This is what I think is the exciting thing. So, summary. The solutions for the two largest caveats from CHAP 2016 study are histogrammer, which is available on GitHub, you can use it, and Spark root, which allows you to read the root files directly in Apache Spark. And the next step is performance tuning, and then do the big thing, because if you want to read 1 petabyte, if you do the math and you have about 5,000 cores, it's about 55 to 60 gigabytes per second that you have to serve if you want to reach 5 hours. So there's a lot of work to be done, partial reads, pruning, filtering, all of these things to make this happen. All right, thank you.
An example of time. Yeah, Gordon.
So part of getting to improving the time, you're talking about partial reads and other. So is some of that limited by the fact that you're using this root connector? You had originally talked about importing the data into ACFS and then reading from there. Could another file format further improve readout times?
I cannot exclude that. Yes.
Okay.
Yes. If you optimize further the file format for exactly these network reads, maybe. But that was kind of what we saw when we talked to people about our first attempt when we did the conversion. That is, they really didn't like the conversion. They wanted they wanted to stay with their root input files and just read.
Yeah, no, that part I understand. It's just trying to understand. All right, thank you.
Can I just ask what Spark is?
Apache Spark is a MapReduce implementation that is open source, that I think was developed because Google didn't open source their MapReduce implementation. So it developed out of Hadoop, and then Spark came, which is doing a lot of more memory caching. So Apache Spark is the thing industries right now.
And so, like, it would MapReduce when you're trying to just copy information from one place to another, or like in what part of the process of, say, an analysis is that kicking in?
So you can think about this the following. If you have a lot of data and you only want to look at, for example, objects of a certain quality, like you have muons and you want to have muons above 20 GeV, then the first step is that you can distribute that over 1,000 nodes that look at parts of the data and filter out the muon, and then you reduce it or merge it together to have one plot. That would be a quick method.
But it's the analysis itself. It's not a data management
it's the
layer. It's the actual data analysis. You go in 2 plots, right?
Yeah, exactly.
Okay.
But in an analysis, there's a lot of like non-event-based data, like calibration constants, your neural network weights and stuff like that. So how would you integrate that? Is it like you distribute that also as a Hadoop data set?
So this is a very good point. So what we did as a first step is we started with something that has all of that done. So you take all the reconstructed information that has all the calibrations and alignment applied, all the data that you need in addition is applied, and from that point on, we wanted to quickly and interactively interact with a lot of data.
But so, do you have a feeling how that is done, maybe in industry, or are there tools that allow you to MapReduce?
Jim wants to say something.
Yeah, so to directly answer your question, if you wanted to use something like a machine learning algorithm in your analysis function, that's all really built into Spark. So, for instance, if you need to refer to some non-event data to interpret your process or event, it will see that your function closes over that variable, serialize it, and send it with your analysis without you even telling it.
Okay.
Any other questions? Okay, well, I look forward to reading more about it in the proceedings. There's still time if you want to ask.
Yeah?
Yeah.
Okay, no, it's just my curiosity. Please slide 10, please. Please slide 10.
Slide 10.
Yeah.
Coming up.
What's the goal?
Different sample. Different Monte Carlo sample.
Okay.
So we wanted to demonstrate that, I mean, it's not only one Monte Carlo sample that you use, because in analysis you need a bunch of different samples and you need to process them maybe differently. So that's why a very quick demonstration is just take 2 different Monte Carlo samples, run it through Spark, and make this combined plot.
Okay. So the point is that you could have even more samples.
Absolutely. Absolutely. Absolutely.
Okay, let's take that one.